We have been talking about a lot of different pieces with these sequences and series, right? And I think part of it, because it's my first time teaching this through, has not probably felt like it's totally meshed. Like, it's meshed with the information that you knew from Algebra 1. I think you guys picked the stuff up that you already should have known pretty quickly. But I think the new stuff is kind of all over the place. So today what I'm hoping to do is kind of bring it all together. So we'll see how it goes. Now, we're going through technically the 8.4 slides where we're finding, like it says, the sums of infinite geometric series, which we kind of started yesterday. But again, I've put a lot of review and changed the worksheet a little bit in hopes of bringing it all together. So we don't have a warm-up. We'll go through our learning targets. So first I want to start with what we've learned so far. Now this would probably be a good slide or even a good chart to put in your notes at some point because this does break things up pretty well. And I know we've talked over a lot of this, and even yesterday we did like a quick review where I got feedback from you guys, so it might be a little bit repetitive, but I do quickly just want to talk through the points there. We have, this is on Canvas. You can get a nice screenshot of it. And now you've got a nice picture on your phone for your background. We have two different types of sequences and series, right? Arithmetic is the first one that we looked at and what we're very familiar with. That's where we are adding and subtracting, and the common difference is D. Now, we use this formula right here to write an equation. So I can tell you, find the 127th term, you would plug it in, and we could find what the 127th term was. Now, we started out writing our equation in this form, but what did we have to do to it to get it in final answer form that we wanted? You guys remember? Solve it. Well, we had to simplify it. Yeah, we had to distribute our common difference, and we wanted to rewrite things so that it looked a lot like what? What other type of equation did it look like? Yeah, it looked a lot like our slope-intercept form. Good. Now, what we haven't talked about as much is this next equation with this next bullet point, finding the sum of an arithmetic sequence. So if we have some type of sequence, 2, 4, 6, 8, 10, 12, and we need to find the sum of it, here's the equation we would use to find the sum of that sequence. Again, we've used it a little bit, but not a lot, and I don't think I've made it super, super clear that that is our go-to for an arithmetic sequence. Questions about any of that? Again, you saw everything except for that last equation for the sum of an arithmetic sequence. You saw everything in Algebra 1, so I know it's repetitive. And we've talked about it over the last week. Now, our other type of series or sequence is geometric, where we are either multiplying or dividing, right? No, we don't divide. Good job. We always multiply, but we may multiply by a fraction, so that would be when they're decreasing. We have a common ratio, which is R. This formula you've seen before, finding the nth term. So I can tell you, find the 127th term. You can plug it in, and we're good to go. Now, finding the sum of a geometric sequence is, I don't even know if we got to it. I know I showed a slide with it on it. I don't think we talked about it a lot. But if we want to figure out the sum of a geometric sequence, here would be the formula that we use. And we're going to use this a little bit more today, if I'm thinking correctly, but definitely go through all this stuff tomorrow with our review. Now, one thing I didn't talk about is the fraternity that we are all in, right? Sigma. Now, if I told you if we had an arithmetic sequence, 2, 4, 6, 8, we'll say 10, and I told you to write an equation in sigma notation, how do we even start to do that? You guys remember? What do we look to do? And it keeps going. Well, we find the difference, yep. So we know it's 2. But how do we even start to write an equation in sigma notation? So we would need our first term. What I'm trying to get at is we would write an equation for a sub n, right, for finding the nth term. Once we get that equation, instead of just leaving it a sub n equals, remember we put sigma in front, and we had our starting value at the bottom, and that could be any variable that we use, I, k, n, whatever, and then whatever our ending point is here. If we want the sum of the first 10 terms, we'd go from 1 to 10. If we want the sum of the first 20 terms, we'd go 1 to 20 or whatever it might be. So that would be a 5-minute review of everything we've talked about so far. If you followed with me through talking through that, and if that even seemed, like I said, boring, repetitive, whatever, then I'd say you're in pretty good shape. Any questions before we move forward? Good? Not good. Good? Okay. Now, what we started to talk about yesterday, and this moves more towards 8.4, is a partial sum. So what we're looking at today is like the sequence in the box, an infinite geometric series. Now, we talked about a type of series that we cannot take the sum of. What was the deal with that? What did we talk about a little bit yesterday? Right, an exponential growth. So all of these go on forever. That's one thing, they're infinite series. But we can't take the sum of a series that is exponential growth like this. Why can we not take the sum of that series? Right? Right, because it'll be infinity, right? You'll keep adding more and more and more and more. It would never end. Now, when we look at a series like it says in the box, consider this series 1/2, 1/4, 1/8, 1/16, all that kind of stuff. Technically, that doesn't end either, right? But like we started to talk about yesterday, it'll get closer and closer to a certain number, but it will never go over that certain number. And we're going to clarify that a little bit today with number 1 and number 2. So the idea of a partial sum just says we can't find from 1 to infinity of this series. But the partial sum, we can get pretty dang close by finding the partial sum. All right? So if we look at number 1, now there's new directions in the homework. Let me There's new directions in the homework, and let me explain them a little bit. In exercise 1 and 2, find the sums for I equals 1 to 5. So we want to find the sum of the first 5 terms. Then from 1 to 10, 1 to 15, and then from 1 to 20. So here's what I should see on, well, before we can do that, if we look at number 1, we look at that series. What is happening between each term? Times 1/2. So our rate would be 1/2. And then our first term is 1/3, right? Before we can start to sum the first 5 terms, like the directions say, then the first 10, 15, we have to write an equation. And remember, for a geometric series, our equation is in the form, we have a sub 1 times r to the n minus 1. So we found a sub 1, we found r. Now we can write our equation. And we'll just use I because we're taking the sum. And like the first part of the directions say, we want to find the sum from 1 until 5. So that's what we are going to look to do first. Go ahead, use your calculator and find the sum from 1 to 5. And read me first couple, yeah, Faith?
I don't know how to do that.
Oh, right. So hit math. Turn your calculator on. Hit math.
I got it.
0. So that now we get into the summation. So our variable can just
But you did it wrong.
starting at 1, going to 5, and then you can just plug this in. Hit enter, and it'll give you the sum of the first 5 terms. Now what you should have gotten is 0.6, 3 repeating. Now we're going to the next part of the question. Find the sum from I equals 1 to 10. So if I were you, I'd scroll up, hit your old one, and then just change the 5 to a 10. So you don't have to type the whole entire thing back in. Good. You guys know what I mean? Scroll up, hit it, put 10 in instead of 5, so we don't retype. We're all good. Now, same thing. From 1 to 15. So take the sum from 1 to 15. And then the last one, by now we should see what number this is approaching. Now we can see, like we did on the first one, we did the sum of the first 5 terms, right? Then we did the sum of the first 10, 15, 20. So as we are taking, we would consider each of these taking a partial sum. And as we take a larger and larger partial sum, we get closer and closer to what our limit is going to be, or where this maxes out. And what do we see it's getting closer and closer to? 2/3. Yep. Now, you could, in our calculator, you could take the sum of 1/3, 1/2, I minus 1 from I equals 1 to infinity, or even instead of putting infinity, you could put like 10,000 or something really close to infinity. But then your calculator spins and spins and spins and loads and loads and loads. So it takes forever to try to calculate all those. So we want to try to look at these early on terms to figure out where this is going to limit out at, or what the max is. And we talked about a little bit yesterday, and it says in our definition here, that a geometric series may approach a limiting value. Well, like we see with these decimals, they're getting closer and closer to 2/3. They're approaching that limiting value. So that would be what our sum is. That's what our limiting value would be. Do we answer that full question? Oh, then describe what happens to the sum as I increases. Well, as I increases, the sum gets closer and closer to 2/3. So that would be describing what happens. Are there any questions on that? I think that, and we're not going to have to go through this process every single time. We're going to have something that's going to help speed things up. But this gives you an idea of what's going on when we do a formula later.
Why don't we just go instead of like starting at 5, just go to 1?
Right away? Well, I wanted you to, I mean, you could, but I wanted you to see how it gets closer and closer to 2/3 as the sums increase. Did you put like 10,000 in? Yeah, it's going to spin for, you're going to have to just reset in the back.
It won't load?
No, it won't. All right, why don't you go ahead and do number 2. Same type of thing. You need to find the sum from 1 to 5, 1 to 10, 1 to 15, 1 to 20. And you should see what they are approaching. Yeah, I'm not sure why it doesn't want it in that form. Oh, because you use X here and I.
Is it 2/3?
So we need these variables to match.
It's double.
Is that the...
It's going up by 1/5. X is whatever your equation is. That would be 1.
something about how you put those parentheses, which I'm not exactly sure why. Mine has parentheses on
Go outside for bookends.
so maybe if here you put another set in at the end of all of it, then maybe that makes the difference.
Okay.
Dude, see what answer.
One before the 1/3 and one after.
I really like your
Let's see what happens.
That's fair.
You're calculating.
You have math?
Okay, we know how to do that.
How about it?
Yeah.
What'd you get for the first?
Stop!
The first what? The first sum?
Why would I delete that?
13.0
Annie, you need to chill.
and then some decimals past it. Hey, did you guys get all your sums? 1 through 5, 1 through 10, 1 through 15, 1 through 20?
First stop. Your A sub n. How do you turn into a fraction?
Just go to like 4 decimal places, unless it's obviously something that's a fraction. Like, is it something that you know
it's
is
a continued fraction, so I don't know if you want
I have like
What's a fraction?
like these are all fractions. Like what's your exact? Alright, you're like your first equation, you know. So A is 5.
You can hit the math, rate frac, and that'll do that.
Okay. Wow. Okay, so then you do backwards.
Your equation should be 5 times 2/3 raised to the I minus 1.
So I use X.
Okay, that will be okay.
So what are you doing for your first like thing on the top of the backwards?
1 to 5.
1 to
I want you to
5?
find the sum from 1 to 5 first.
Okay.
Then 1 to 10. Then 1 to 15, 1 to 20.
Did I do this wrong?
Why?
Your first one should be 13 point something. Your first sum. You raise a 3 to the power. You need to raise the whole 2/3. You guys get them? First.
Did it wrong. Hopefully you guys
If you sum them all up, then get an idea in your head of what you think is approaching. What number is it getting closer to?
The x minus 1.
You should be able to see, especially in the last 2 terms, the 2 sums. The last 2 sums.
Mm-hmm.
You guys get that?
1.3.
So what I was talking about earlier, what I would do is instead of retyping it,
I don't know.
this. You can do whatever you want. That might be a little bit quicker. What's our basic one?
Oh, I have the x to the 5.
Answer.
2/3. Oh, I like this. Just like right?
That's
That's right. Now, when you want to find the sum from 1 to 10, just go back and change the 5 to 10. Hit enter. The first one should be 13 point something.
I got 1 point.
13.0247. Oh boy. What'd you put in your calculator?
Why is there a second 5?
You didn't put a parentheses.
Oh, Ryan. It sounds like
You're raising it 3 to 2/3.
You know what I mean? So
to the denominator.
Wait, we're going on a field trip in
I don't think it's today, but I think just in general, you get to go out to that one property. Yeah. No. He didn't know if it's different from the others.
Oh.
So it's going to be 10.
See, I already got it.
I should have told him that. Well, let's take the age test. I put a box. I put one in.
Dude, you have to get 48%.
The math part. Or the
That's
real
already?
48%.
He was right. They ignored that.
It wasn't kicking.
I drive a tractor.
Select it. There's 1 through 5. 1 through 10. You guys good? You good? Well, I got 1 through 10. So, I'll take it for a ride. Oh, you gotta dig.
It's all like this.
Second something that goes through and find it. Hit infinity, it's gonna spin and spin and spin. You can put like 100 million in there.
So you put this right here, so that's 10.
Yep.
So 5 times. So 2 would be the second one.
This side is not that side.
Alright.
I know you guys aren't all totally finished. Here are the 4 values. 1 through 5. We should have gotten about here. 1 through 10. Hey, stop embarrassing Ryan, Keelan.
There's no gun.
1 through 15. 1 through 20. Now, from 1 to 5, it makes a huge jump, right? The sum of 1 to 5 is all the way up to 13. Now, from 1 to 10, not a huge jump between 5 and 10, right? Not a huge jump between 10 and 15. Not a big jump between 15 and 20, right? We're just moving a little bit, a couple decimals between the sum of 1 through 15 and the sum of 1 through 20. So that tells us that we're getting really, really close to 15, which is our limiting value. Yep. And we would say that their limiting value, that's the sum of, what was that series? That would be the sum of that series in number 2. 5 plus 10 thirds plus 20 ninths. We would say the sum is 15. Okay? Are we understanding that a little bit better? I think that helps clear some things up. All right. Now, we can do all of that and get a pretty good idea of what the sum is of some type of series or something like that. But if we want to do something a little bit quicker, we can use this formula here. So if you look at number 3, well, if you want to jot down that formula on your homework piece of paper in your notes or whatever, that would probably be a good thing. The sum of an infinite geometric series. Now, before we look at number 3 and while you're getting that jotted down, the directions. In exercise 3 through 8, find the sum of the infinite geometric series if it exists. When does the sum not exist again? Exponential growth. What would be going on with our rate in exponential growth? Well, okay, but what specifically would our rate have to be? Over what number? If it's greater than 1, we would have exponential growth, right? Or if it's greater than negative, yes, negative 1. We also need to be careful. We'll look at some examples, don't worry. Less than negative 1, sorry. It could be greater than negative 1. So let's take a look at number 3. Now, again, if we try to, oh, it's not up there. If we try to punch infinity in our calculator, if you can find where that is, it's going to spin forever. Forever and ever. But if we use our equation, we can find the sum really quickly. So we want a sub 1, or our first term. What is our first term if we are looking at this summation. It's 7. Yep, we know that a geometric series goes in the form a sub 1 times r to the n minus 1. So 7 is our first term. 1 minus, what is our rate? 1/4. So we can plug that into our calculator. What did you get? 9.3 repeating. Now, part of this, did you guys not get that? So you need to punch in your calculator 7 divided by parentheses 1 minus. Yep, and I would make sure, I would just put 0.25. Yep, that would be 9.3 repeating. That also would speed it up a little bit. Now, something that they want to teach you in this unit, and which will show up on the test. If you hit math, if you have 9.3 repeating in your, if you got that as your answer, and you hit math fraction or math enter, that should give you 9.3 repeating as a fraction.
Yeah, what? Math fraction.
Yep. Did you find that? Math. And it's the very first one. It says math frac.
Oh, you said this.
That will give it to you as a fraction.
No,
We've known this for a while.
This was like 3 units ago.
It's okay. All right. So that's how we can find the sum of these infinite series. Why don't you go ahead and take a look at number 4?
Already on it?
All right. Then we will do number 5 together. I think whoever gets number 5 should get a sticker.
Oh, I want a sticker.
All right. Well, or number 4. Sorry, number 4.
Got it. Got it.
I got really called first.
Let me see. Wrong. What? Then she got wrong too, because she said they I have a different answer than both of you.
Oh,
Not
never mind.
What?
It's
What did Smee get?
Wait.
That's
That's what I
had.
had. That's what I had. You thought What do you have?
Awesome.
This game is.
She got my attention. I don't know what to tell you.
I literally circled it doesn't exist.
Literally,
This game's.
sorry. I'm sorry. She had my attention. That's all I'm saying. She had my attention. Good job. Yes, it's exponential growth, right? It's 5/4. So we cannot find the sum. D and E. I hope you're kidding. It is not -12. Exponential growth. All right, let's look at number 5. That was fun. Let's look at number 5. How are we going to find what our rate is?
Look at it. Subtract the.
Subtract. I'd look more to divide.
Okay.
How are we going to find our rate? What are we going to put in our calculator to find our rate? Or you could look at it and probably figure it out, but no, this is geometric. It would be. What did you put in your calculator to find that, right?
I just did 1.8, which is 95.5.
There you go. So we've got our first term, second term. If we take our second term and divide it by our first term, that would give us the rate.
When did I say that? Like,
You said like subtract or something.
oh, well,
So is it?
Paul
Is it?
understood.
Is it 3 cents?
I heard you.
I think 3 cents.
Yep, it is Trey. Good job.
Yes.
Good job, Trey.
That is R.
Now our first term is 3. So we know that the sum equals our first term over 1 minus our rate. We can punch that into our calculator. Yep. It doesn't make a difference to me on the test. The test is all multiple choice almost,
Let's go.
Yeah.
and it will be in fraction form most of the time on the test. So you need to.
It's like a simple decimal, like 7.5. You have to put that.
Well, if that's the case, like I said, the test is pretty much all multiple choice, except there will be like I'll give you a summation and I'll say write this out in long form. We'll go over it more tomorrow, but if it's like 0.75, the multiple choice option would be 3/4
Okay.
most of the time. All right, you now have enough knowledge to do the rest of this worksheet, which is not too much. It is.
Wait, here's the same exact sheet.
I changed the top. I changed number 1, number 2, the directions. I didn't even change the numbers, just the directions. So I'll go over this and then I'll put some music on and play. With it, you're fine. With look at number look at number 6. I would rewrite it, and if you look at the key, I rewrite it like this.
That's what I put on my top.
So the second term is -4.
Right.
Time. 1. 2/3.
I would rewrite those. I like to rewrite those at least as plus or negative.